Welcome to Chemistry 111. Here we're going to finish Chapter 9 and start Chapter 10. But first, to finish Chapter 9 and talk about the upcoming lab. So, last class, we talked about molarity and that molarity is moles over liters, and that we can get this by, if we can find our moles and divide by our volume, we can get molarity. Then we showed how we could dilute something by using the fact that the moles of the initial solution were equal to the moles of the final solution, and set an equation that simply said M1V1 equals M2V2. The molarity of situation 1 times the volume of situation 1 equals the molarity of situation 2 times the volume of situation 2. Finally, we briefly discussed titration, which uses that same M1V1 concept, that as you titrate an acid to base, we're looking for the exact point where the moles of acid equal the moles of base. In that particular instance, in that instance alone, we can use that MAVA equals MBVB, which is simply the M1V1 equals M2V2. Basically, it's just a different way of saying the same thing, but MAVA is the moles acid times volume acid equals MBVB. That's what we're going to be looking at. That's what we're going to be using. So this last slide of the chapter is all about utilizing this. So how I do these equations, how I do most of the problems, if I'm working this out, is I write down what equation I think I might need, write down all the information given. The most important part on these problems is to try to establish what you're given and which numbers are which. So let's read the problem completely first. 15 ml solution of HF is titrated with 0.125 molar NaOH after 43 mils of base. Then point has been reached. I was saying something along the lines of, ideally, in a perfect world, you'll know that HF is the acid because it donates the proton. NaOH is the base because it has the hydroxide. But even if we didn't know which one is which, let's use context to try to put these guys together. 15 mils of HF is titrated with 0.125 M. So we know 15 mils is associated with one. 0.125 molar is associated with the other. So we are adding the NaOH to the HF. We're adding the NaOH to the HF. And then the next section says after 43 mils is added. So we're must be adding the NaOH. So real quick, let's put down everything we know. We have Ma. We don't know what the Ma is. The question asks for that. We know Va is 15 mils. We know that Mb is 0.125 M. So off chance that's what killed my power. And Vb, now that we've established that, 43 mils. So plugging in everything we know would say reestablish Ma equals 0.125 M times 43 ml over 15 ml. ml and ml cancel. The units we would be left with is molarity. So doing that quick multiplication, 0.125 times 43 divided by 15. So 0.125 times 43 divided by 15 is 0.358. 0.358 molar. Jumping back, problem 2. The second question, a 20 mil solution of NH3. Technically, that's the base. You may not know that's the base, but 20 mil solution of NH3 is neutralized by the addition of 8.2 mils of 0.95 molar HC2H3O2, which is acetic acid, which is vinegar. So what is the concentration of the base? We have a volume. We don't know if that the volume is the acid or the base, but we do know 8.2 mils of one concentration. We know these two are associated, and I want to know what is the molarity of the other one. So we can easily, the thing most people have problems with is they don't associate the right things together. Even if you don't know this is MA and VA, if you associate this M1 and V1, and that's V2, you solve for the only one you're not given. That's how it's always going to be. So MB is equal to 0.95 times 8.2 mils divided by 20 mils. Mils and mils cancel out. Normally, I'd say turn them into liters. Turn them into liters. But as long as the volumes are in the same units, it will work out in the end. 9.5 times 8.2 divided by 20 gives you 0.3895, which should technically be rounded to 39. This is a lot of buildup for this is the last slide of this chapter. Sorry for that great inconvenience, but that's all of this chapter. So done. We're going to start opening up the next chapter. In the meantime, so let's talk about the lab. The lab, what we're going to have to deal with is a titration lab. We're going to take vinegar from the bottle. We're going to dilute it by a factor, I can't remember, a factor of 10, I'd like to say, perhaps. But we're going to take X amount of volume, maybe it's 5 mils, maybe it's 10 mils, I'm trying to remember, and dissolve it in a total of 50 mils of solution, I think. You think we'd take 10 mils and dissolve into 50, or maybe it's 10 mils into 100. I'd have to double check. I'm going to go prep that in a bit. So we're going to dissolve that. So we're going to dilute the acid. Then we're going to use that acid in 3 different titrations. We're going to use a set amount of acid, set volume that we're going to know. We're going to titrate with a base that has a set concentration. And we're going to determine at what volume of base does the moles of acid and moles of base equal. Once we've achieved that, then we can find how many moles of acid were there. Once we know the moles of acid, we can find out, once we know the moles of acid, we can find out what's the molarity of acid? Once we know the molarity of acid, we can find out what was the molarity of acid in the original bottle. And that would be the idea. The hardest part, math, it will not be the math. The hardest part will just be the setup. Once you get it set up, once you get the titration, the burettes ready and all that, it'll be titrate, boom. It will not take the whole lab. And the thing that most people get tripped on is the undoing the dilution. But I will be there. I'll be able to help you as best I can. It will not be a hard lab. It'll be a semi-fun lab. You got to see some cool colors made up by when you add acid to base. Okay, I now have the next set of slides up. So let's go to thermochemistry. So this is a chapter all about energy and the energy of reactions. This first little bit will not be a whole lot of math, but eventually we will get to how do we calculate the energy of reactions, how do we calculate calorimetry, and the calorimetry and energy reaction stuff will be the topic of next week's lab. So, okay. Start off with some basic definitions. The thermodynamics is just basically the study of energy. That and heat. The thermo right there. What is energy, though? Energy is the ability to either transfer heat or to do work. Now, we all know what it means to do a hard day's work. We're students. You're doing a bunch of grade. You're doing a bunch of homework and all of that. But in physics terms, work is explained as a force applied over a distance. Typically, it's mechanical work. When we think of work, we think of a piston expanding, which can be used to turn a crank or something like that. That's the most common form of work. Now, there's lots of different types of energy out there. We're going to focus on only one or two types of energy, but there are more than that out there. There's kinetic energy, which is the energy of motion. While all atoms have it, because all atoms are moving, we don't really worry about this too much, especially in this chapter. Kinetic energy is mass times velocity, but this is something more in the physics realm. Potential energy is the stored energy of, like, I put something here, it has potential energy. If I drop it, potential energy is turned to kinetic. Potential energy for us, though, could also be a spring loaded, ready to spring on, like on a mouse trap. Or it could be a chemical bond, energy stored, ready to be used when the bond is broken. There's also electrical energy, but the main energy we'll talk about related to heat and work. Heat and work. So the energy of units, we can see little calories, big calories, and joules. Joules is the SI one, the main one we will use, but just quick. A calorie is physically defined as the energy it takes to heat 1 gram of water by 1 degree C. So it's a way we can measure, like, if I were to eat this cereal, how much energy would it give me? Well, if I was to burn that cereal, I could heat the water. That same energy could be used to heat water 1 gram, 1 degree per calorie. So 100 calories would be, you could heat 100 grams 1 degree, or 1 gram of water 100 degrees. Capital C calories is 1,000 calories. It's like saying a kilocal, which I don't know why they didn't just do kilocal instead of capital C calories, because they want it to be confusing, I guess. But joule is the main one we'll use. Joule is thought of as a force applied over a distance, and the force is usually a mass times a velocity squared, mass times acceleration. So a joule is actually equal to 1 kilogram meter squared per second squared. Just like moles, molarity was a mole per liter, a joule is a kilogram meter squared per second squared. But typically, we're just going to leave this as a joule. Okay. One of the main things we will have to consider as we work our way through this is both system and surroundings. The system and surroundings. We have to consider where the energy is coming from, where the energy is going, and so the signage of what the energy is. Almost always, we will be looking mainly at the system. The system is the place where the action is taking place. In the case of a chemical reaction, it is the reaction itself within the molecules that are reacting. Now, the surroundings are defined as everything around the system. So in the case of a chemical reaction, if it's two solids reacting, it would be the beaker they're in, the air around them, the whatever is around the beaker, the table. If it's a solution, which remember, a solution means the atoms are dissolved in water. The water is part of the surroundings. So when the solution heats up or cools down, it's because the system is either absorbing or producing or absorbing heat. But in terms of energy-wise, if we add both system and surroundings, we encompass the entire universe. If I took this room that I'm in right now as the system, everything around this room, which includes the rest of the Earth, all the solar systems and whatnot, and the galaxies would be the surroundings. But the reason why we need to consider system and surroundings is because the transfer of heat Q or work W will either be to the system from the surroundings or from the system to the surroundings, and will have a positive or negative sign based on this energy exchange. Because we're looking at, if I run around, I'm super hot and sweaty, and the heat radiates off my body. So I start with, say, 500 joules of energy. And after heat radiating off my body, 200 joules of heat leave. They go into the cold air around me. I've gone from 500 joules to 300 joules. I've seen a decrease in energy of 200 joules. When energy is released out of me, I see negative heat. So negative Q of 200 J. When you have negative Q, it means it's exothermic. Exo means the heat is exiting the system. Heat is transferred out. Now, same way, I jump into a sauna or a hot tub. I jump into a hot tub, and suddenly heat is flowing into me. I'm getting a lot hotter because the heat from the hot tub is flowing into my body. I'm seeing a net increase in heat. So it would be endothermic. Heat is going into the system. So you're seeing a positive or a negative sign based on whether heat's going in and out of. When work is done by something, a piston expands, pushing a crank, we'd say it'd be negative work. Work is done by the system. But when you compress the piston back down, work has to be done on the system. And so you'd see an increase in work. So this is really important. And that's because of the first law of thermodynamics. We'll probably end it on this slide, mainly because we're about out of time. I hate that this is as far as we got, but this is as far as we're going to get, and I'm not going to hold you after. But okay, so we need to consider the system and the surroundings. When we combine the system and the surroundings, the net change in energy is zero. the truth of this, the first law of thermodynamics, we kind of discussed this previously, but energy can neither be created nor destroyed. It has to come from somewhere, or it has to go somewhere. If I'm running around, I get super hot and sweaty, heat leaves my body. Where does it go? To the surroundings. If I'm in a room and the room is the surroundings, heat goes into the room. If I'm considering the room the system and the room is poorly insulated, heat flows out of the room to the surroundings. You're giving off heat. But if you consider it, the heat lost by the room is equal to the heat gained by the surroundings. If I add that negative Q and the positive Q together, the net change is 0 to the universe. Energy is conserved. If I'm doing work on something, something is absorbing that work. The net change in energy of the system might be negative. The net change of the surroundings may be positive, but the net change in the universe is 0. So the idea energy has to come from somewhere. So one of the things we will consider, one of the first things we'll consider is internal energy, which is simply the sum of all types of energy in the system. We won't look at an absolute internal energy because that means nothing to us. I could give you, we have a bajillion internal energy units in our body, but that means nothing because we don't have something to base it off of. But what we will look at is the change in internal energy. When this action is done, how has the energy changed for the system? Because we're going to be looking at the change in the final minus the initial. Whatever the final was versus whatever the initial is, we get the delta U, which is the change in internal energy. And it's really going to be adding the heat and the work components together and seeing how has the energy changed. But that's where we're going to go. Meantime, that's where we're going to stop. I just want to maybe say one more thing. And it's gone. Okay. If I think about it tomorrow, on Friday, I'll bring it up Friday. But in the meantime, I will see most of you in lab in the next 2 days. So